Right. So one of the things I want to focus on today, and we'll get to this in just a minute, is how to write a proof. So this is going to be how to write a mathematical proof. So how do you write a proof as opposed to, how do you think about why something should be true, right? And so this is like one of the important topics for this course. So, overall, I mean, there's a lot of important concepts that we will talk about, right? But some of the general things that we will learn is how to prove something, but also how to write a proper mathematical proof, right? And those things are a little bit different, and we'll talk about this in a minute. I also want to say that, so on the course information, the last page of the course, several people were asking about this. On the last page of course information, there is right. So there's a note. There's a note for the class that I write, and I try to write them in advance, a couple of days in advance, and then I try to go over it the day, also to make sure to find typos and things like that. So that is more readable. So if I were you, I would first read the lecture notes that I post after the lectures. And then there's also on the last page of the course information, there is, and I try to do this in advance, but it's a little bit difficult to do it in advance. So it's say the date, and it's say some keywords from the lecture on that date. So over the weekend, I posted it for the 2 lectures for this week. But then I go back, I will try to go back, so I actually went back this morning and changed some of it from the second lecture so that it fits more. And I think I will only, I give references there to the book, and initially I was thinking of giving both references to Rudin and to the main textbook. I think it's probably just, I think it's probably smarter just to give it from the main textbook. Okay, but Rudin is a great book. This was a book that was created here long time ago, and it is like a classic in the subject. It's a great book. It's more formal than the other book. So the other book is a little bit more accessible. And so that's why we're using that. But actually, Rudin is a fantastic book. If it was just myself, I think Rudin is hard to beat. But the other one is more accessible, and so it might actually be better the first time you learn it. But so I think from here on out, so I deleted the references I had to Rudin. I think I would just give references to the main textbook, but I certainly encourage you to look at Rudin. Also, I also encourage you to look at chapters that we will skip, but there's also things that we initially skip and then we come back to. But again, you should, it's like when I list the things that we will cover in the lecture in advance, it's only sort of approximation, right? Once I write the lecture, it might be slightly different. Okay, so we had, so last time we talked about the theorem, we didn't prove it, that the reals is a complete ordered field. Right, and so in particular, it was an ordered set that was also a field, and it was complete, right? And so again, complete meant, so if you had a subset A here, which was a subset of R, then A is bounded bounded from above. If there exist M in R such that for all A in A here is less or equal to M. So, and then if that's the case, then we say that an M here is said to be an upper bound. For A. Likewise, if A here is a subset of R, then we say that A is bounded from below if there exists little m in R such that M here is less than A for all A. Okay. So this is upper and lower bound. Okay, and several people ask on Piazza, they ask, you know, they were a little unclear about you know, where does this M, capital M, where does this have to be? In what set does it have to be? And likewise for this little m, right? And so let me try to give you some example, and I try to do that on Piazza, but let me just because several people were asking about it, let me just say again, so that this capital M, when you have it like this capital M does not need to be in the set, right? A is bounded, so here's an example. If you're looking at the set 0, 1, so this is the interval, but it does not contain 0, and it does not contain 1, but it contains everything in between 0 and 1. This one here is bounded, so if this here is A, and we think about A here as a subset of R, then A is bounded. And so one usually say it's bounded if it's both from above and below. Right, so if one just say that it's bounded, then one means that it's bounded from above and below. It's bounded, and right, and so because like bounded from above, because you have that if x here is in this interval, then of course x is less or equal to 1, right? In fact, it's strictly less than 1, right? But you see, this set here, there is no element in this set that is an upper bound for this set, right? The upper bound is outside the set, but it is in all of R, and that's fine, right? An upper bound will typically just be in the larger set, and the same with lower bound. Now, everything on this board except this theorem, but you know, this in terms of ordered sets, right, has nothing to do, you know, it's just much more general than R. So if S here is an ordered set, and A here is a subset, So it's an ordered set. So it's a set with an ordering. And if A here is a subset of S, then again we can say that A is bounded from above if there exists M. Again, M does not have to be an A, but it can be just in the larger set, so that for all A in A, it's less or equal to M. Right. So this is like the definition in general, being bounded above if you have an order set and you have a subset, right? And now just to illustrate it, so typically we're going to think about where the set is R with the usual ordering, and you have a subset of it, and you talk about whether it's bounded from above or below. But of course, you could also do it in a more general setting like this, right? And so here's an example that if you look at, which maybe is counterintuitive, but if S here is the half line, so it's all the real numbers between say 0 and infinity, and then you would have A here is a subset 0 to 1. Right. Now A here and the ordering. So this is of course a subset of R, but you should forget about R. I mean, you know the ordering from R, but forget about it because this is now what you think about the set S, right? And so if you're looking at A as a subset of this, then A here, A is bounded from above. Right? Why? This is just because for all A in A, you have that A here is strictly less than 1. So 1 here is an upper bound for A, right? But now think about, does this set here has a lower bound, right? Well, a lower bound have to be inside this set S, right? Because we're thinking about this here as a subset of this ordered set. We don't think about it as a subset of the real line. But if you think about it as a subset of this set here, then there is no lower bound, right? Because 0 is not in this set, and no negative numbers in this set. So this here, and this seems maybe a little bit counterintuitive, but A is not bounded from below. As a subset of S. Obviously, it is bounded from below if you were thinking about it as a subset of real line. But if you think about it as a subset of S, it's not bounded from below. Okay, so another person was asking the infinite and minus infinity. Those are not real numbers. Okay. Yep.
So on the homework, should we consider like all of the keys as subsets of R?
Sorry?
For like question 3 on the homework.
Yeah. If it's not directly stated that it's not directly stated that there's a set S, and then it has to be a subset of that set, right? Then it would be assumed that it's R. Yeah. Of course, you're welcome to ask on Piazza. I don't have the homework here, but I would say that you're safe if it's not stated directly what the larger set is, then you can assume it's R, because we're going to concentrate mostly on R. This is another distinction between Rudin and this book that is the main textbook. Rudin is more abstract than the main textbook we are using. In particular, the main textbook here, and I'll do the same in my lectures, is that a lot of things are motivated from R, and then you abstract afterwards. So whereas Rudin starts with abstraction and then it specializes to R, and of course there's an argument for maybe starting with a familiar and then abstract instead of doing the other way around. Okay, so right, and so for whether it's just an ordered set, I mean, just in general. So remember that completeness. So completeness, so this is when you have an ordered set. So if you have an ordered set, and A here is a subset of S that is bounded from above, then if it is complete, if S is complete, so if S is complete, then any subset that is bounded from above has a least upper bound. Then A has a least upper bound. Okay, and that least upper bound is denoted by the sup of A, right? So this thing here, it has the property that A is less or equal to M for all A in A, and also if M1 is another upper bound for A, then M is less or equal to M1. So that's a least upper bound. Right? And the same thing is, so similarly, when we have an ordered set, and we have a set, if it's complete, and if we have if A here is bounded from below, then inf here of A is the least upper, is the largest, the greatest lower bound. For A. Right, so this again means that this number here, little m, so m here is less or equal to A for all A in A. And if M1 here is another lower bound, then M1 here is less or equal to M. Right? So this is the symmetric property. And so again, R, the reals, is complete. So whenever you take a bounded subset of the real, so if it's bounded, that means that it's bounded from above and below, then it has a least upper bound and a greatest lower bound. Okay, and those are denoted by sup and inf, right? And in general, sup and inf are not in the set itself, in the set A, right? I mean, there could be, but in general, there wouldn't be. Yeah?
The example that we talked about where we
Yeah.
did the open set
Yeah.
committees, that is not complete.
That's right. No, so if you're looking at this set here, right? So suppose that this here is the set S, then, and if you take A here, is a subset of S, and A here is bounded from, let's say that A here is bounded from below. Right? If it's bounded from below, then it couldn't be this set here. This here is not bounded from below, right? So it sort of means that if it's bounded from below, then A here could not have numbers that was approaching 0, right? And so actually, if it is bounded from below, if it's a subset of this and it's bounded from below, then actually it would have a least lower bound, greatest lower bound, right? You should mean. Yeah. So it is. I mean, I'm not going to prove anything is complete or not complete, but it's pretty convincing that it is actually complete. Right? In this sense, there's some other sense that is not complete, but anyway, in this sense, it is complete. Yeah. No, it's a little bit. It can be confusing. Later on, we'll talk about maybe some other notion of completeness, and then it's not complete. But in this notion, it is complete. Okay, so the next thing I want to get to is this with how to write a mathematical proof. Okay, and so and again, I mean that's a super important thing to learn in this class, and it's not just a formal thing. I mean, yeah. I mean, it may seem like a formal thing. Why bother with that? But it's really, really useful. And the more complicated things become, the more useful it is. And so I want to illustrate this with how to write a mathematical proof. So I'm going to illustrate this. So we will illustrate it by proving again by writing a formal proof of y square root of 2 is a real number. So I want to write, so last time we talked about that square root of 2 was a real number, but when we proved it, it was more like we talked about the idea. And so then the question is, so if you have, like, you imagine you have a piece of scrap paper, what we did last time was what you would be writing on the scrap paper. So I want to talk about, if you were handing it in or showing it to somebody, then you wouldn't do that. You would do what we do now. Right? But it doesn't necessarily make for a formal proof doesn't necessarily make for a great lecture, because it's kind of formal. So let me try to explain how you should write this. And again, this is a very simple example, but hopefully it will give you an idea of what to do. And again, this is a really important part of this class that you're bound to use in many other classes later on. Okay, so let's first talk about what was square root of 2. So square root of 2, this here was a number, and it was given by that it has the property that it's positive, and when you square it, then you get 2, right? That was what square root of 2 was. Now, so we want to prove, so this is the theorem. So theorem, square root of 2 is a real number. So no, maybe I should write it more formally. There exists alpha greater than 0. There's alpha in R with alpha greater than 0, and alpha squared is equal to 2. Okay. Now we look at the set A. The set A is the numbers, it's the x such that x is positive, and x squared is less or equal to 2. Yeah, so x here, and so now I was specialized to the real numbers. Okay, so that was why I didn't actually write it, but you're right. It certainly can't hurt. Okay, so that's the theorem. And so now we try to write a formal proof. Observe first that A here is non-empty since 1 is in A. Right? 1 is positive, and when you square 1, you get 1, so this is definitely less or equal to 2. So A here is non-empty. Next, observe that A here is bounded. It's bounded from above. In general, by the way, when you write a proof, then you really only try to establish the properties that you need, because otherwise it's confusing. If you establish all kind of other property that is not needed, that just makes it confusing. So it's bounded from above. And this is just because since 2 is an upper bound. For A. Okay. Now the next thing is, so now we have a non-empty bounded subset. So we set alpha equal to the sup of A. And we want to show that alpha is positive and alpha squared is equal to 2. Well, right, by definition, the way we defined A, all the elements in A were positive. So by definition, 0 is a lower bound. So you for sure have that 0 here is less or equal to, well, it's actually, I mean, even 1 is a lower bound. So you can also just say that 1, since 1 is a lower bound, since 1 here is in A, you also have that this alpha here must be bigger or equal to 1. Right? Because it was supposed to be an upper bound for A, so in particular. Now, and so we have that alpha is less than 1, and it's the least upper bound, and 2 was an upper bound, so you have this. Right? Since maybe I should write, if you write it with this, since 1 is an A, we have that 1 here less or equal to alpha. And since alpha is the least upper bound, and 2 is an upper bound, we have that alpha is less or equal to 2. Okay, now remember, I mean, we're going to do it exactly like we did last time, but we're just going to write it down in a proper way as a proof. Right, so remember that last time we then divided the proof into 2 steps. The first step was so part 1. So all we need to prove, maybe I'll just say that, all we need to prove to show is that alpha squared is equal to 2, right? Because we already have it as positive now, because it's bigger than 1, right? And so there was 2 parts to this, to step 1 and step 2, or part 1 and part 2. The first part was, so part 1, we will show that alpha squared is less or equal to 2. Right. And so we prove this, so assume not we will show that that leads that this leads to a contradiction to that alpha is the least upper bound. For A. I mean, I'm writing everything out here, right, just to illustrate it, right? As you get more and more familiar with this, right, then the structure is the same, but you know, some of these steps will seem almost too trivial, and that's probably fine, right? But of course, it's always good to err on more details than fewer details. Okay, so this is what we want to do. So we assume not, so assume that alpha squared is strictly bigger than 2, right? Then, and this is where it sort of deviated more from how we did it last time. And that's why, you know, what we did last time is really what you want to have on the scrap paper. I mean, that's what we did last time was like the idea. And then once you see the idea, then you try to write it as a formal proof, like what we do now. And so assume not set h equal to, so I'm going to set h equal to alpha squared minus 2 over 4 alpha. Okay. Right. Obviously, if this was like the first time you would do it, you wouldn't just come up with this sort of thing, right? I mean, this is coming from the scrap paper that you have, right? So you're setting h equal to that. And then you observe that since alpha here is bigger than 1 and alpha squared is bigger than 2, since that, right, then the numerator here is positive and the denominator is positive. So h here is positive, right? You also have that h is right. You also have automatically that that h is, maybe we don't need that. Let's see if we need that. So okay. So now you set alpha 1 equal to alpha minus h. And what I want to prove is, so we want to show that alpha here, alpha 1, is an upper bound. For A. So I want to prove that this is an upper bound for A. The first thing I want to do, if it's an upper bound, it does need to be positive. So let's check that. So since we already have that h was positive, so this here was h was positive, alpha squared minus 2 over 4 alpha. Right, this thing here is less or equal to, I can even forget about the 2, so you can write it as alpha squared over 4 alpha. And so this here is, I can just divide by alpha, so I get alpha over 4. So I have, since we have that h here is less than alpha over 4, then alpha 1 is bigger than is bigger or equal to 3/4 of alpha, right? Because I'm subtracting at most alpha over 4, and so there's still 3/4 of alpha left, right? So I have this in particular, this thing here. It's actually bigger than 3 over 4, but I just need it to be positive. So it's positive. So alpha over alpha 1 is positive. Now I'm looking at alpha 1 squared, right? So alpha 1 squared is equal to alpha minus h squared. So this here is equal to alpha squared plus h squared minus 2 alpha h. Okay? And this thing here is less or equal to alpha squared. Here, h here is, so now I like to say that h is less or equal to 1. Actually, I'm going to use that it's less than a half. And why is that the case? It's actually alpha itself. We already know that alpha was less than 2. So you have that this thing here is less or equal to 2 over 4. So this is equal to a half. Right? So now I have that. Now I have that this thing here is less than plus. I just use that it's less than this thing here. Right, this here I think it's fine to just use h here. I could use h over 2. Maybe I'll use h over 2. So one of the h I just replace by a half. That is an upper bound. And the other one I just keep. Right? So I have that. And then minus 2 alpha h. But if you multiply alpha by h, then it's disappear in the denominator. So you're getting minus 2. And then you're getting alpha squared minus 2 over 4. Right, and so here you get, this here becomes alpha squared plus, and here I'm just writing in, and I think it's, at the moment we're sort of overkilling it here. And so I can replace this one here. So, right, let me just write it in. Alpha squared minus 2 over 2 times 4 times alpha, right? And this thing here is alpha squared minus 2 over 2. This 2 cancels with one of those 2. So this is what I have. And so now I get that this thing here is so I get that this thing here is we are adding it here. So this thing here is alpha squared. So let me just bring these two together. Let me just maybe I'll just combine all of these. I don't think I need it this well. Right. So if I combine these two here, I think I'm fine with just having a 2 here, 4, sorry, instead of the 2. So if I if I do that, then I get alpha squared. Maybe I should just bring it on the common denominator. So this here, this alpha, sorry, I'm getting rid of. I'm bounding this from above by alpha squared plus, and I'm going to just make it easy for myself. I think it's fine to just use that alpha is bounded by 1, and then you can just bound it by alpha squared minus 2 over 4. And this thing here is alpha squared minus 2 over 2, right? Here again, I'm just using that alpha was bigger or equal to 1, right. So, and then I just actually ignore this 2, right? So this is definitely an upper bound, right? And so now you see that this thing here is equal to alpha squared. This thing here, you can think about this thing here. You can write this thing here, if you will, as alpha squared plus alpha squared minus 2 over 4 minus 2 alpha squared minus 2 over 4. And so what you get is that it's alpha squared minus alpha squared minus 2 over 4. Right? And this thing here is now, this thing here is positive, right? Because alpha squared was strictly bigger than 2. This is positive, so this is strictly less than alpha squared, right? And so this here would also, which is still, right, this is, right, so this thing here is also an upper bound. That's not, sorry. No, I need to, no, sorry. Okay, so I have this. No, sorry about that. Okay, so, yeah, no, sorry. Okay, let's just go over this again. Sorry. So what I'm trying to prove here, right? I'm trying to write down the formal. I mean, that's a problem, that it got so formal that I was now in. So what I'm trying to prove here is that I want to say that this part one is that alpha squared is less or equal to 1, right? This is what, less or equal to 2. That's what I want to prove, right? This is part one, right? And so I assume not. So I assume that alpha squared was strictly bigger than 2, right? If alpha squared was strictly bigger than 2, here you have 0, here you have alpha, and now we define this alpha 0. Alpha 0 was to the left, so to speak, of alpha, because it was subtracting a little bit. And what I want to show is that this alpha 0, I want to show that this alpha 0 is also an upper bound. So I want to prove that this square here is also bigger than 2. That's what I want to prove, right? Right? So I want to find a lower bound, and that lower bound should be 2. Right? So this is not exactly what I wanted to do, okay? So let's just go through it here. That's right. So this here was correct, and this here is really for the second part. Okay. So we define it like this, and now I say that this thing here is bigger or equal to, but I want to bound it from below. And so then I can ignore the h squared. So it's bigger than, because that's positive, so it's bigger than alpha squared minus 2 alpha h, right? And this thing here is, so this is equal to alpha squared minus 2 alpha. I fill in what h was, this here was h, right? And then you see that this here cancel with that, and this here, and you're getting alpha squared. This is this alpha squared minus alpha squared minus 2 over 2. And this thing here is equal to, this is equal to alpha squared over 2. This is subtracting that. And then you're adding, right? You're adding 1. So this is what it is, right? Alpha, we have already proven that alpha here was bigger or equal to 1. So this here is bigger or equal to, I claim that this here is bigger or equal to 2, using that alpha is bigger or equal to 1, right? And so you see that alpha 1, that is a smaller number because you're subtracting a positive number from alpha, that is also an upper bound, right? So this is contradicting, so this contradicts, and then one often writes this symbol here. This is a standard symbol that means this is a contradiction. Yeah?
You say using the alpha is greater than or equal to 1.
Yeah.
What if alpha is 1?
Yeah, then you get 2, but that's fine. I just needed to show, all I needed to do was I needed to prove that I have that, so you see that I have that, I'm assuming that this thing here is strictly positive. And then I define alpha 1, but alpha 1 is strictly less than alpha, right? And then I have that alpha 1 squared is bigger or equal to 2. This here means that alpha 1 is also an upper bound. This is strictly less than alpha. This was supposed to be the least upper bound. That's a contradiction, right? And so you see, I fell into the trap. I was doing it so formally that I lost track of what I was doing. So I was actually in the process of proving I mean, that's a danger with, but the formal proof is much easier to read afterwards, right? And so you see the difference here with the formal proof was last time we sort of did a little calculation, and then we tried to figure out what should this h be, and then it sort of came at the end, right? But when you write down the formal proof, then you would sort of up front, you would already have done that little calculation, and you would up front say what h was supposed to be, and then you would kind of run through the argument, right? Yeah. Sorry?
I was just confused because I plugged in alpha equals 1 last time.
Here, so if I mean, of course, alpha is much bigger than 1, but I'm just using, I'm only need here that alpha is bigger or equal to 1 to say that this thing here is bigger or equal to 2.
I think you need it greater than 2, right?
Sorry?
Alpha squared is 2.
This is, right, this is alpha. So the inequality here is that alpha 1 squared is bigger or equal to 2. And I'm using that alpha at this stage here to conclude this inequality. I'm using, sorry, no, you're right. Yeah, sorry about that. You're right. I'm using that alpha. No, I'm not using that. I'm using that alpha squared is bigger or equal to 2. Yeah, sorry. That was what you meant. Yeah, thank you. Okay, so that was that was a formal proof of part 1, and then there's part 2. So the other inequality. So how do we do that? And when you write this, it's always good to try to explain what you're going to do, and in this case, what is going to be the contradiction. So let's try to prove part 2, and hopefully we get it straight this time. So, so part 2, so I want to show that, so we have part 1 was establishing that alpha squared was less or equal to 2. Now we want to prove, so part 2 want to show that alpha squared is bigger or equal to 2. Okay. And so, again, we're proving this. We will show this by contradiction. So, assume that alpha squared is strictly less than 2, right? And now I think it's helpful. You don't necessarily have to do it, but I think it's helpful if you say, maybe it's too long, but it's at least helpful to think about where is the contradiction coming from. So if alpha squared is less than 2, so I will say it, you don't necessarily have to write it, but indeed, we will show that if this is the case, then there exists some numbers alpha 2 bigger than alpha such that alpha 2 squared is also less than 2, contradicting that alpha is an upper bound. For the set A we defined. Okay, that's what we would prove. Okay, and so we want to find a real number that is larger than this, but still the square is still less than 2. Okay, and so in this case, I'm going to So now we sort of do this, the structure is going to be the same. We had this little scrap paper where we sort of outline the argument and figure out what h had to be. And so I'm going to use this h. So we're going to, again, maybe I'll just erase this here, so we don't get confused with the first part and the second part. Okay. Okay, so I'm going to set h again. I'm going to define it very similar to what I did before. But now I have to remember that I'm assuming that alpha squared is less than 2. So I define h to be 2 minus alpha squared over 4 alpha. Okay, this is how I define it. And then what I'm interested in is, so I have here 0. I have this that is supposed to be the upper bound, but I want to prove that that really isn't an upper bound. That's an element in my set A, and so this is this alpha 2. So I'm set this and alpha 2 equal to alpha plus h. This here was just to illustrate. You don't necessarily have to include that. Okay, and I want to show. We want to show. I think it's a good idea to write what you want to show. In particular, if I really had written that before, then I wouldn't have been in trouble, right? Because I'm trying to prove something else. So you want to prove that alpha squared here is also less than 2, right? So this is so so we already have that alpha here is positive. It's it's bigger than 1. So this number here, this here, we already know is bigger than alpha. Okay. And so if I can prove that, so this here is, so this bigger than alpha, if I can prove that the square is less than 2, then alpha here, would not be an upper bound, right? There's another element in the set, A, that is bigger, okay? So I want to prove that. So now I'm looking at alpha 2 squared, so that is alpha plus h, right? That's how I define alpha 2, and I square it. And if I do that, then I get alpha squared plus h squared plus 2h alpha, right? And I now, so now I want an upper bound, right? And so we already have that alpha is this one here. H is, you see that H is in this case here. So H is equal to 2 minus alpha squared over 4 alpha. Alpha is bigger or equal to 1. This here, the denominator is bounded by 2. So again, it's 2 over 4. So this is bounded by a half. So H is positive, and we have that H is positive, and H is less than a half. And so now this here I can bound. I can bound trivially by just using that H is bounded by 1. So I get this plus H plus 2. And then H times alpha again, or 2H alpha. This is, when you multiply this by 2 alpha, then the alpha cancel out, and the 2 cancel with one of these, with 2 in this 4. So you're getting 2 minus alpha squared over 2. Okay, and so now I get that this thing here is bounded by, so H here. H is also a very rough bound for H. Is so I have that, and now using that H here is equal to alpha 2 minus alpha squared over 2 over 4 alpha, which is less than 2 minus alpha squared over 2, since alpha here is bigger than 1. Right, so I have that. Right. So using that, we have that alpha 2 squared is less or equal to, let me just write that line, I'm just now filling in, alpha squared, the H here, I'm using this inequality here, 2 minus alpha squared over 2, and then I have the same thing again. And so you see that this here, it's this here times 2, so this is just alpha squared minus 2 plus 2 minus alpha squared. And, and this inequality here, there was one of these inequalities I should have replaced by a strict inequality. This is because H is positive and is strictly less than 1. So this here is actually a strict inequality. So this here is a strict inequality. Okay, but now you see that this thing here, the alpha cancel out, and you're getting 2. Right? So you have that alpha 2 squared is strictly less than 2. That's what we wanted to prove, right? And this gives that alpha 2 is also in A, and yet alpha 2 was bigger than alpha, and this is the desired contradiction. Okay, so again, you know, we already did this last time, but the point here is that how do you write down a formal proof, right? And a formal proof in this case is that you try very clearly, in this case it was divided into 2 steps. So you try to divide it into the 2 steps, and then maybe you have a last line that say that, you know, part one and part 2 together show that alpha squared is equal to 2, completing the proof. Right, and again, the point here was that, so we already knew how to prove this, but like how do you write down a formal proof, right? And so for this proof, it was divided into these 2 steps, so you try to write each step separately. They were both of the 2 steps was proven by contradiction. And so you would say up front, you would say that you're going to prove it by contradiction. And then, of course, there would be, the statement that you want to prove, since you're proving it by contradiction, you would assume the negation. And then I think if you can, and it doesn't feel too much, I think it's very helpful to write what you are trying, how you are trying to get the contradiction, right? That's what I tried here, right? And then you see, then the big difference from when we were trying to figure out how to prove it is that you now go ahead and you just define the things. You define H and alpha 2, right? That sort of seems to come out of nowhere. And then you establish the property that you want to prove that leads to the contradiction. Okay, that's sort of the structure. Are there any questions to this? Yeah.
What property of the real numbers are we using for this sort of script? Is it that like
so
number is real if it's at least upper bound of a set?
Right. So we're using a few things. We're using, we're using a few things. We're using that is ordered. We're also using something about that is an ordered field. And why? Because we're using something, well, we're using something about multiplication to at all define square root, right? And also we're using something about that 1 is bigger than 0, right? And then we're also using, of course, completeness in order to define this least upper bound, right? So we're using a bunch of these things, right? But of course, if you have, if you're asking when, and that's not really, at this stage, like very, very soon, in one of the next few lectures, things will be in the real numbers. We're not going to work on general fields. And we're not going to, general fields, this is not part of this subject. But of course, it's interesting to ask. And you see, and I think that your point is like, when can you define something like a square root of 2 in a field, something like that, right? And there's a lot of things, you're absolutely right, that there's a lot of these things that was just sort of general property. But maybe we shouldn't get too much into that. So I wanted to, there's a few more things I was hoping to do. So I also wanted to just talk about the Archimedean property again. And so I wanted to, again, just outline how to write a formal proof. And again, and the reason, of course, why I'm illustrating how to write a formal, writing a formal proof is an important part of this class. And I'm obviously using the things that we already proved last time, just so that you can kind of focus on how to, not the statements, why the statement should be true, but just how to write it. And so let's talk about the Archimedean property. And so the Archimedean property just saying that, so this is the theorem, that the natural numbers is not bounded from above. Right. That's one way of formulating it. Right. You could also say, like we did last time, that whenever you take a real, there's a larger natural number than that real, right? Right, that's the same. Okay, so now how do we prove this? So again, here we're thinking about things as being subset of R. Right? We always, when we don't really mention it, then we always think about it as being subset of R. And so we will show this by contradiction. By contradiction. So suppose alpha is an upper bound for the natural numbers. Well, we can assume, after replacing alpha by sup of A, we can assume that alpha is the least upper bound. Right. So, and now, and then I think it's nice again to write where the contradiction is coming from. So we'll show we will get the desired contradiction by showing that that alpha minus 1 is also an upper bound, contradicting that alpha was the least upper bound. Okay, and so now since alpha, so this is what we want to prove then. Since alpha is an upper bound, for all natural numbers, if you add 1 to the natural number, this here is also a natural number, right? N plus 1 is also a natural number. So n plus 1 must be less or equal to this upper bound, right? But this implies that n subtracting 1 on both sides implies that n is less or equal to alpha minus 1. And this, which holds for all n, all natural numbers, so alpha minus 1 is also an upper bound. Okay, and that's and this is the right. This gives you the side contradiction. Okay, so that's how you would write that. Let me talk a little bit about sequences, and so this will be a big topic. So sequences. So, well, first, so we talked about that a little bit. So if you look at the, so how do we think about of square root of 2 on the real line. I mean, so the way to think about square root of 2 is what we did here, that it's this positive thing so that the square is 2, right? But if you want to place square root of 2 on the real line, then you could think about it as a limit of a sequence. If you take 1, and then the 1 is less than 1.4, which is less than 1.41, which is less than 1.414, etc. Right, and so this here is a sequence. I'll make that precise in just a minute, but an increasing sequence of numbers, and the limit is square root of 2, right? So if you plug square root of 2 in on the calculator, it will bring out a lot of digits, right? And these are the first digits, and it will continue on. And that's how you think about square root of 2 if you want to think about it on the real line. And so we want to, and so square root of 2 is going to be the limit of these, and we need to make this precise, and we also need to make precise what really a sequence is. So a sequence of real numbers this is a map. It's a function from the natural numbers into R. So for each natural number, you get a real number. And so, right, so a function, it is, a function is defined by the value at different points. So this thing here, but if you want to think about it as a sequence, then it's common to denote this here like that. So this is how one typically write a sequence, where instead of the, what the argument is, what this here is, inside a bracket, you write it as a subscript. Okay. So this is a sequence, and so in the case over there, if you're thinking about A1, say, to be equal to 1, A2 to be equal to 1.4, A3, and now I'm thinking about the sequence here as I'm thinking about square root of 2, and I take the number of, the subscript here, I'm just taking the number of digits in square root of 2. So now I need 3 digits. Here I needed 2. 1, 4, 1. A4 is 1.414, etc. Right? And so, then you have, then AN here is a sequence of real numbers, and it's actually increasing, that the sequence AN is less than AN plus 1. We have this property. And we want to talk about next time, we want to talk about what does a limit mean? What is a limit? And so square root of 2 indeed will be the limit of this sequence. And the limit you write like this sometimes as n go to infinity of AN. But we'll talk about this next time.